the slant is a constructivist slant. In other words, I'm leaning on that side in this whole series of lessons. I believe that that's one of the ways that children learn some of the stuff better. In the math wars between constructivism and skills, I am in the middle though. I do believe that they need to memorize things and stuff like that. But I think that both things should be done. This whole series of lessons though, the students, this is what the students are going to get. Paper like that. They're never going to have anything written on the paper. They're never going to have a list of problems. It's not going to be like that. Everything is going to be on the slide, what they need. The way I'm going to go about the presentation, you're only going to get one example per lesson. So this presentation is for teachers. But it's just to give you an idea of what kinds of things you would be doing with the students daily, on a day-to-day basis, and how you can get to complex mathematical knowledge real quick and solidly. Okay? That, of course, the students may still need to be presented with this material in other fashions. But the other thing is that it is very eclectic in the kinds of mathematical content that comes up. The aim of the lessons is to get to Pythagoras' theorem and irrational numbers, to make sense of these things, to see them in a kind of concrete model, except the model is the xy plane. It's not really concrete, but it's concrete enough. You can see it, you can cut to pieces. It can be brought down to a level of second and third grade. So that's the other thing, that it has a lot of other stuff, but the aim is irrational numbers and Pythagoras theorem, so that's what it gets emphasized. But at the same time, the students are reviewing and learning other mathematical things. Okay, so this is a hands-on lesson. You're going to have to do what the students would be asked to do with me as we go along. Okay, and in the first day, we're going to work on finding the area of a square. So now I ask you to please draw that square on the xy plane. And I'm going to do the same thing over here on these xy planes that I have. These are copies of the paper that you have, and I'm going to do the same thing that I'm asking you to do. Can you see?
Where did you get those?
Where this is a poster making machine that you feed it that, and it gives you this.
Did the district pay for it?
And did I what?
Did the district pay for that?
Oh yeah, the machine, yes. Okay. Everything here belongs to the district. So I mean, we're getting better at some of these things. Yeah, that's a very good question. You know, these kind of things that I have here are not available easily to every teacher, but math teachers can easily get their hands on this kind of stuff. You know, my math teachers all have laptops, and right now this projector belongs to District H, but they're going to buy me one. I'm a math coach, and they're going to buy one for the department. So there's going to be 2 or 3 available at my school just for the math teachers. Okay? Hopefully by the end of the year, maybe we can have 10 of them, or 5 or 6, whatever. You know, but it's getting a lot better in that sense. So we're going to draw the square. So please draw the square on the xy plane.
It's just like a large print, isn't it?
It's like a copy
So you
on
can,
thermal paper.
these things go on and off?
Oh, those are post-its, yeah.
Oh, they're
That's the other thing.
Post-its.
They're post-it dots.
God,
Yeah, they go on and
technology's
on.
great. These are Post-it
They
dots.
go on and on.
Son of a- Thank you.
Here's the presentation. Oh,
No. In my class, I have one of these laminated.
oh yeah, that's if you laminate it,
filming it,
it's even
sorry.
better.
No.
Huh?
Are you
The
filming?
Only
thing
the
that you
instructor.
do is you just-
Only the
you
instructor.
take it.
Oh, good.
Oh.
So, yeah, that's another thing. You can laminate these, and then you can write on them with, with whiteboard markers.
What I do with my students, I have the Cartesian coordinate system, printed in a transparency, print plenty of those. And what I usually do is, because I want my students to participate, I hand out the transparencies with a marker, and then they do the work, and then we share that with the class, with a projector. That's another way, because I don't have a poster.
Right. Yeah, for example, when you're doing this with the students, I would have a student do this. Okay? But right now I'm going to go through lessons kind of quickly. So I would have an overhead calculator over here and a student punching numbers in it whenever it's necessary. I would have a student that finished doing his drawing come and do this on the board, so that they get off their chairs and participate. Now, so the main thing here is that you want to find the area of this square by inspection. This whole activity is going to be that kind of activity. So what I mean by that is that I'm going to have this square right here, and I'm going to say the area of this square is 1, 2, 3, 4, 5, 6, 7, 8, 9. The area of that square is 9 square units. This is a square unit, and this square is formed by 9 of those square units. Can everyone see that? So we have the area. We're building the understanding of area because students in the middle school and even at the high school level, they still don't quite understand what area means, right? And all these lessons are going to have this. I also threw in the perimeter just to keep practicing the difference between the area and the perimeter. So I'm going to find the perimeter of this square, and I say, what is the size of this side? And someone will say that it is 3. So it is 3 of these units. This is a unit of length. This is a unit of length, and this is a square unit, a unit of area. So the area of this square is 9, but the perimeter is 3 plus 3 plus 3 plus 3, which is 12. By inspection, right? So that's what we would do in the first day. Lesson 1, day 1, they would have, of course, 4 squares, for example. 4 squares to draw. And find and complete a table like this. Okay? Day 1. Finding the area of a square, reviewing perimeter, talking about units and all kinds of stuff over there. Day 2. Again, please draw the square. Do you notice anything different on this square from the one that we did yesterday? Now it has fractions, right? So it has fractions, mixed numbers. So we'll have to draw this square again, and I'm going to draw the square. Please draw it on your paper. One of the things about this work is that it's self-checking. If it doesn't look like a square, something must be wrong. Because I'm saying draw the following square. So the students get to check their own work almost. And when you walk around the classroom, it's easy to see if a student made a mistake, right? If they have a rectangle or some kind of trapezoid or anything like that, you say, you know, check your points, you know, something's wrong with your points. So now we want to find the area of this square by inspection. Can someone tell me what the area of this square is? What is
20 and
it?
a quarter?
19.
19?
Well, I'm counting all of them. I'm counting.
Okay.
I'm
19
counting.
and a quarter.
I'm counting the whole squares, and I say 1, 2, 3, 4, 5, 6, 7, 8, 9,
20 and a
10,
quarter.
12, 13, 14, 15, 16.
20 and a quarter?
And then
Any more
4,
bits?
16,
4 by 4
17,
is 16,
18,
17,
19,
18,
I have 20 and 1 quarter.
19, 20, 20 and a quarter.
20 and a quarter. So let's say the students, they can't figure it. So I'm going to show them how to do it by inspection. I'm going to say, there are 16 complete squares in there, right? Can everyone see the 15 complete squares? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 complete squares. And then these over here are halves of squares. So 2 of them make a whole square. Does everyone believe that? That if I get 2 halves and put them together, I'd make 1 square? Yes. So these right here make another square, another square, another square, and another square. So I have 1, 2, 3, 4. I had 16, and then these pieces right here are squares made by halves. So that's 4 more. And then I have that interesting piece in there, right? What kind of a piece is that? Well, it's part of a square unit. And what part of a square unit is it?
But it's 1/4.
It's 1/4 of a whole unit. So the area of the whole square is 20 and 1/4. So now, from yesterday's activity, you remember that after we did a whole bunch of squares like this one, we found out that if you multiply this number by itself, you can find the area of the square, right? You remember that from yesterday? So I'm going to check and see if it works with this problem. What's the size of this side?
4.5.
4.5. So let's see if it works. 4.5 times 4.5, I hope gives me the area of that square. So this is how I multiply mixed numbers. I say 4 times 2, 8 plus 1, 9. I convert the number to halves. This is the same number. And when I multiply fractions, all you have to do is multiply the numerators and the denominators. So I get 9 times 9, 81. 2 times 2, 4. So I have 81 divided by 4, but 81/4, I don't know, I mean, I don't want to count 81/4 here and see if it works. So I want to turn that into a mixed number, right? And this is how you turn an improper fraction into a mixed number. You divide. So after dividing, I find out that this is 20 and 1/4, so it works. If that's too much for the class, I have a kid over here doing it on an overhead calculator that multiplies fractions. That means a TI 73 or a TI 83 with the overhead, projector showing it over here, and the students will believe that it's true, right? Because the calculator did it. You have to make sure the input is correct and all that, right? So this is another chance for the students to participate, or it's another chance for you to review multiplication of fractions, mixed numbers, and such things. But you're not going to dwell on this stuff. You're just going over it to show them that it works. Okay? So that's the second day lesson. We're learning to find areas, but they're a little more complicated, right? They have fractions in them. But it's very easy if a student struggles with this, you can come to the student desk and show the student in his drawing, right? This is 1/2 and this is 1/4. You see that? This is 1/4 of the whole square and so on. So you can show the student that, right? On their paper that they made, right? So that's day number 2. So let's move on to day number 3. What are we going to do now? Again, no formulas, no... Yes?
Do you go also over the perimeter?
Yes, yes.
Okay.
Yes, I mean, it's there just to keep emphasizing the difference between the area and the
And
perimeter.
the focus at this point is area.
Well, because we're working on Pythagoras theorem and all that stuff. But yes, of course, you have the examples here for them to say, okay, well, now we're going to find the perimeter. Remember, the perimeter is when you go around the figure and add the sides. So the perimeter has to be 4.5 plus 4.5 plus 4.5 plus 4.5, or 4 times 4.5. Another opportunity to review how to multiply, right? So, but you would want a student to come up here and do things like this, for example. You wouldn't mind a student coming up here and saying, well, this is 16 and this is 1 and this is 1, so it's 80. You know, I mean, that would be great if a student came up here and did that. It's great, right? You could say, is that the only way of doing it? No, you could multiply. But they may be happier doing this than the multiplication, right?
Do you require them to, as they find either the area or the perimeter after day 2, to do it in 2 different ways, one that is graphical and one that is computational?
No, at this point, I'm not
It's only
doing computation.
Okay.
Yeah, I want to continue on this model because everything that I prove and explain has to be understandable at a very low level. If you have the calculators for them there and you say, well, notice, you do say, notice that is, you know, notice that the answer is 4.5 times 4. Let's see, 4.5 times 4, yes it is. You know, that kind of stuff. But you see, you want them to do it however they can. Because you're not concentrating on the computation.
Even if they change it, for example, to improper fraction, like 9.5.
Right. But remember, we want them to do understand these modes. You know, so that because things are going to get complicated. Okay? You saw how they already got complicated here, right? This is nothing yet. Okay? This is day 2. So now they complete the table. They can check with each other, you know, how did you get that? Well, I got it like this, look, with this, that kind of stuff. So now, let's go to day 3. Yes?
Yeah, all along, is this supposed to be individual work or they are allowed to?
It's individual work, but there's no problem with talking or anything. They can, in the worst case, when a student is struggling with graphing and finding the points, you say copy your partner. Because I want the student to have the drawing in front of them so that when I explain things, they have the drawing. Daily, they're practicing with graphing in the graphing points in the coordinate plane. But if at first they're not good enough, I can say, you know what, he has it already, copy it from him. because that's not the lesson. But you can see how after a couple of weeks of doing this, they'll finally get how to find the points, right? It's teaching that stuff like sideways, you know. I mean, at the beginning of this, of course, you did an explanation of the coordinate plane, how do you find points, you know? And then this is nothing but practice and practice and practice about that. It's an apprenticeship mode of learning, you know. But they're practicing in context, right? They're doing complicated things while practicing how to plot points. Okay? So now we have day number 3. Day number 3 looks kind of like day number 1, except they're called dancing squares. So please draw these squares on the xy plane so that you see what I mean by dancing. Be very careful with the coordinates, please. So again, these squares are a little more challenging now, right? You know, you have to be real careful with the coordinates to make sure that your squares actually come out squares, right? I mean, and because they're not sitting in this comfortable position that we did the last couple of days, you know, it's a little more confusing. You just need to be careful with your coordinates, and at the end, you should have two squares that look like this. This is the way your square should look on your paper. Yes? Okay, so now again it says find the areas by inspection. Wow. It doesn't look like a trivial matter here now, right? So I'm going to jump ahead on my slides to a place where I have a coordinate plane so that I can show you how to find those areas by inspection. Okay? Again, technology. Isn't it this great coordinate plane? I'm going to write on it, I'm going to erase again, I'm going to write on it again, erase. I can use it as many times as I want, right? Nothing happens to it. So the squares that you're working with look like this. This is one of them, and the other one looks like this. Now, there are two ways that I thought about that I can find the areas of these squares. One of them is an additive model. The other one is a subtractive model. So I'm going to find the area of this square in the additive mode. So I say I have 1, 2, 3, 4 square units right there. And then these two halves right here, these pieces right here are halves. So these two halves are going to make another one, right? Another whole square. These two halves, and these two halves, and these two halves. So I have 4, 5, 6, 7, 8. Everyone believes me that the area of that square is 8 by adding the pieces? Okay, that is the additive model. Now I'm going to show you over here the subtractive model with the other square. What I do is I make a square outside my square that I'm working with. I made a big square outside of it, and I say, what is the area of the big square? Can you tell me the area of the large square? The area of this large square is 25. But I want to take away these pieces right here, these regions. I want to take them off. Now, can you tell me what is the area of this one triangle right here? By inspection.
One of those triangles and then
What?
inside. Two of them.
What's the area of this triangle?
2,
Why?
because it's half by inspection.
Right, by
It's
inspection.
half 4.
It's half of 4. Right? There are 4 square units right here, and this triangle is half of that. Very believable, right? So this is 2, 4, 6, 8. 25 minus 8 is 17. Yes? So the area of this square is 17, and it's acceptable, right? How I found it. This is, I found it by subtraction, this I found it by addition. The area of the first square is 8, the area of the second square is 17. Is everyone comfortable with that? Now, let's look at this. In the previous 2 days, in the previous 2 lessons, we noticed that if you want to find the area of a square, you multiply the length of one side times the other, and you get the area. Like in here we said 3 times 3 gives me the 9. Over here we say 4.5 times 4.5 gives me 20.25, and we checked it and it did work. So now, over here, there must be a number that if you multiply it by itself, this times this, you get 8. And there must also be a number that if you multiply it by itself, like this times this, the answer is 17, because that's the area of that square, right? So, but about 2,300 years ago, the Greeks were working with this stuff. They were building squares and trying to find out certain things, just for fun almost. They were working with this stuff. And they believed that there existed two kinds of numbers. They believed that there existed a kind of number like this, and of course this keeps going forever. They believed that there were numbers like that, and they are also work with fractions, with rational numbers. They believe that there were numbers, because notice that these numbers are written with this ones. So they didn't have any problem with this kind of stuff. So when they stumbled upon these facts that we're studying right now, when they stumbled upon this, they said, there must be a number like this, that if you multiply it by itself, the answer is 17. They said there must be a number, because these are the only kinds of numbers. And they believe that at our religion level. They didn't believe it because they were intellectuals. No, they believed that God had made these numbers, and by default, He had made these numbers too. Because these numbers can be written with distance. But they believed that that was it. God was done with numbers. So they struggled for decades, maybe even centuries, to find a number that did this and a number that did this. Okay? And they looked for decades because they were sure about this. Otherwise, they would have stopped looking after a few months, right? But they were sure of this, so they looked and looked and looked and looked and looked, and they thought there must be such a number, but we haven't been able to find it. That's all. But there must be a number like that. But so many years were going by that to continue working on these things, they said, well, let's invent a way of writing this number. Let's invent a way of writing that number. And they invented this way. They invented this way, and they said, this picture stands for the number that when you multiply it by itself, the answer is 17. It's just like shorthand for this number that they were looking for. They say this picture stands for the number that when you multiply it by itself, the answer is 17. This picture stands for the number that when you multiply it by itself, the answer is 8. But it must be a complicated number because we've been looking for it for years and we still haven't found it. Like you do. I still haven't found what I'm looking for. But they kept looking. So, this symbol, we now call it the square root. And the reason we call it square is because it came from this kind of investigation. That's the reason it's called square root. Because this is what created the need for that. In other words, they were looking and looking and looking and they couldn't find it, so they said, well, let's call it something. So they came up with this. Right? So for example, this is the way it works.
Did they actually have the radical notation?
They might have written it some.
Oh, but they didn't have it.
Yeah.
So late.
Right. Yes, they call it looked different. It might have looked like this. was shorthand for them. See, it was, but that's what it meant. This stands for the number that when you multiply by itself, this is the modern look. Yes, you're right. Absolutely. I mean, the numbers didn't even look like this, you know, for that matter. So, you know. So anyway, they said, let's write it like this, and let's move on. Let's keep going. But they knew that they had found out something kind of weird, because they were working on this problem, you know, and they just said, wow, you know, this is an interesting problem. Okay, so we're in lesson number 3, and we already stumbled upon the need for irrational numbers. You see, they are needed because of this little contraption, right? These drawings. Okay? So let's move on. Any other questions or comments about this?
How did you get the graph paper on the PowerPoint?
It's a publisher document. I pasted it on top.
Oh,
It's a publisher.
Scanned, but
It's a publisher document,
uh,
and then I pasted it on.
you mean is it on CD or something like that?
No. The graph paper I created. I created on publisher,
Using publisher.
using publisher,
Okay.
and then I copied it and pasted it on PowerPoint.
But do it in Word too, right?
In Word, yeah. If you email me, I'll send you all this stuff so that you don't have to make it.
That's very kind of you.
I'll send you the PowerPoint presentation so that you can edit it.
I didn't copy your email there.
Oh, well, I'm going to give you copies of the transparent of the slides also. I'm going to give you a paper copy of the presentation, but I'll email it back to you if you email me first. Okay? So three lessons on area, and we already went through the beginning of history to 2,500 years ago, as far as numbers are concerned, right? The need for irrationals. So then, let's go to lesson number 4. So lesson number 4 is an even more complicated dancing square, and I'm going to skip this one because it's the same thing, but it's just more complicated. Okay? So this is kind of optional when you're teaching. If your classes are ready for it, do it. Because what this is, it's a dancing square with fractions. So it's dancing in a really weird position. So it's very hard to explain how to find the area by inspection. But you learn how to find areas by inspection, so you should be able to find out the area. Just for checking purposes, the area of that square is 3 1/4. So please write it down so that when you do it, you know, if you come up with a different answer, you know, email it to me so that I can verify, you know, that maybe I made a mistake. Okay? So again, this is dancing squares with fractions. They're just, you know, more complicated. Day 5. Why were we learning to do areas? Because we want to prove Pythagoras' theorem. We want to prove it so that the students can see it on their paper. They learn how to find areas, so now I want you to draw that triangle. Notice that it says draw the following triangle, and then it says draw squares adjacent to the triangle using the sides of the triangle, meaning this. Draw squares around the triangle using, I want you to notice how I'm teaching the students how to do it. What do you mean? That's what I mean. I didn't give them anything. They have to put it on their paper. And it fits in the first page that you were working. It fits in the fourth quadrant. Okay? This one that I'm asking you to make fits in the fourth quadrant of the paper that you're working with. Okay? So I'm going to draw it over here on my paper. One of the purposes of asking you to do the activities is so that you realize how non-trivial it is. I mean, it is not like busy work, right? It's relevant. If they practice doing these things, they are learning to navigate the coordinate plane in a meaningful way. Okay?
Other things, like for example, when they want to draw the square that's pretty, you know.
It's not easy, right? So then after you let them struggle for a while, you tell them, look, this is the way you do it. 3, 2, 3, 2, 3, 2, 3. That's the easy way.
Or take the rectangle, which is 3, whatever you
Take
want.
the square around it. Yeah, see? 3, 2, 3, 2, 3, 2, 3. So then again, you're asked to find the areas and all this stuff, right? We're finding the area of the triangle just because now we know how to find the areas by inspection. The area of the triangle is 3. It has nothing to do with the other activity, but just so that we can find the area. And we can find the perimeter too later on. And we're going to look at how do you write the perimeter of this triangle, okay? Because it's something new. But first, we're going to find the areas. We're interested in the areas of the squares. The area of the square is how much?
9,
9. The area of the square?
4,
4. And what's the area of the square?
13.
It's 13, right? So if you draw, like again, you know, they don't know the Pythagoras theorem, so you're going to find it by inspection. It's an original square of 25. This is 3, 6, 9, 12. 25 minus 12 is 13. The area of the square is 13. And they're going to do 2 or 3 of these in the paper. So they're going to realize that the sum of these two squares equals this square. And we're not talking about a squared plus b squared. We're talking about a squared. Right? You see what I'm saying? We're not talking about a squared plus b squared. No. We're talking the area of b squared plus the area of b squared equals d squared. Which is Pythagoras theorem in a very concrete way. Yes?
What kind of homework do you assign between these days?
This is, when I'm doing these kinds of things, like I said, I have like these ones, I may have 6 squares. This one I may have 4. This one I may have 3 or 4. This one I may have 3 of these figures. So I tell them to continue working on it at home. But you can see how I can on the side say, draw these rectangles and find their areas in the grid. Right? I can put it over here. This is the homework. They're applying what we're doing in class, but to find other things. I can give them triangles. I can give them right triangles, obtuse triangles, isosceles triangles, and I can tell them to practice finding the areas by inspection. Because every day I'm finding areas by inspection, right? So I can, you have to give them homework that they can do. And that is relevant. If they're doing this in class, they'll be able to do a lot of things. You can actually tell them, draw the following octagon and find the area by inspection. And they're going to go home and draw an octagon. And what do you have to give them? An XY plane, right? And the little instruction, draw, the points. So that's the kind of stuff you would do. So we find that the area that so we tell them that now that's what the Greeks were working on and discovered when they were working with this irrational number problem. Do you notice how that other stuff leads to this? That's how they stumbled upon this other thing. They were working with squares and numbers and and then they come up, you can see how from these things you can easily land over here, right? And then this happened. The square of this is the square. So now we have one proof of Pythagoras' theorem, which those kinds of mathematical topics here and here are the ones that lead to irrational numbers and are very difficult for students to grasp. So hopefully these 2 lessons give them some comfort with that. Yes?
It's also interesting that this really blew their mind. It sort of put paid to Greek mathematics.
Exactly.
One of the reasons was they couldn't measure that diagonal. It was an incommensurable.
That's the thing that they were like. That's why they
be able to measure everything.
they were trying to make it fit their world. They said there has to be a number A over B that does this because there's no other kind of number. And they believed that so strongly that they went on for a while doing this. But so that they could continue these investigations, they created some kind of way of writing it. The number that when you multiply it by itself, the answer is 13. In other words, the square root of 13, right? Now, we found out, so the Greeks were working with these kinds of things, and it turns out that to this day, there isn't a better way of writing the number that multiplied by itself gives you it. We use this way still. This means the number that when you multiply by itself, the answer is 13. Okay? To this day, we call it the square root of 13 because of historic context. It became necessary in a working with squares context. Okay? So, let's move on. Day 5. Day 6. Now, the Greeks were, they kept going. They didn't stop. So they say, is it going to work with other things? So they say, draw. I'm going to go real quick through this. 5, 5. 7, 5, and 5, 9. This is the triangle that I asked you to draw. And then it says, draw 2, 1 rectangles. This is a 2, 1 rectangle. You notice that it is 2 to 1. 2 to 1. This right here is a 2, 1 rectangle. 2 to 1. And do you notice that this diagonal has 2 segments that go across 2 squares? So if this is 2, this is 1, and this is 1. So what I accomplished there is I drew similar rectangles around the triangle. And those rectangles are called 2, 1 rectangles because the ratio of their length to their width is 2 to 1. So the students may have difficulty drawing the rectangles, but after you explain it to them, they'll see it. So now, what's the area of this rectangle? The smallest one. 2. What's the area of this rectangle? 8. And let me find the area of this rectangle by inspection. It's inside a 4 by 5 rectangle. So that's, I start with 20. And this triangle here is 2, 4. This triangle right here is 4. This one over here is 4. This one over here is 1, and this one over here is 1. So I have 4 and 4, 8, 9, 10. So I have 20 minus 10 is 10. So the area of this rectangle is 10. So, wow, it works with that too. It doesn't only work with squares. It works with rectangles and hexagons and octagons and any polygon that you can think of. It works with circular figures. If you draw a semicircle, a half circle here, and a half circle here, and a half circle here, and find the areas, this plus this equals that. And it has to do with the fact that areas always have a component that looks like that. Isn't it true? That's why it turns out that it works with this thing. Anything that you draw here, as long as they are similar, they must be the exact same shape, but different size. These figures that you draw around here have to be similar. If you are able to draw similar figures around the triangle, this plus this area are going to equal this area. And that is an amazing discovery. I discovered this recently while teaching. While reading books about teaching. So this is kind of optional again. Do you notice that I'm going into a little more depth in some of these things? So that lesson again depends on your classes. Okay? But it's one of those things that they keep it interesting for the student. They go, wow, that's like magic almost, right? Just like the Pythagoras theorem blew the Greeks.
That's a sense of discovery.
Exactly. But you build the knowledge to be able to handle it, right? So that's day 6. Now we come. The Greeks said. So wow. So I wonder. The Greeks were thinking about these things, and they say, I wonder how this looks. They ask themselves, I wonder how this looks. The square root of 1, the square root of 2, the square root of 3. You notice that we found some of them already, right? We found out how the square root of 4 or the square root of 8 looks, right? Well, they were wondering about this, and then someone figured out how to do it. Of course, they had already discovered Pythagoras' theorem, and they created this beautiful drawing. This is 1, and this is 1, because the square root of 1 is 1, right? So 1 squared plus 1 squared is 2 squared. So this is the square root. This squared is 2. 2 plus 1 is 3. So this is 3, and this is the square root of 3. Right? This squared is 3. This squared is 1. 3 plus 1 is 4. So this area over here is 4, and this is the square root of 4, which is 2. So this length right here is twice as much as this one. 4 squared, the square root of 4 squared is 4, plus 1 is 5. So this square over here is 5, and the square root of this is 5. So you ask the students to draw this. I mean, you understand how it is drawn, right? You do 1, 1, and you do this. And then this is the square root of 2, right? So then you 90 degrees, another 1, and that's the square root of 3. Another 90 degrees, and that's the square root of 4. So in day 7, you just ask them to make this drawing so they can see how the square root of 1, the square root of 2, the square root of 3, the square root of 4, the square root of 5 looks. This is how they look in real world. Remember, you're going to get this on paper and on PowerPoint. Okay?
It's a very ingenious way.
And the kids, you know, it's because of the artistic aspect of it. They just love it. You know, they draw it and they go home and show it to the parents.
I have a question.
Yes.
The way you have them draw that, do you have them draw that using protractors, just by?
I'm going to have them do it this way. I'm going to show them how. I'm going to have a 3x5 card, for example, a card. And I'm going to say, this is 1. And I'm going to put a mark. Okay? And I'm going to say, okay, this is 1, and the card has a 90-degree corner. So then I'm going to put it right there, and I'm going to say, this is 1 right here, 1 right here, and then I do that. And then I put the card right here, and I mark 1. And then I put the card right here, and I mark 1. And I can make it any size I want.
They don't have to make the right angles themselves. So
No, because the card has the right angle, and the 1 could be anything they want. They can make a little one, and then a bigger one, and then a bigger one. The 1 can be anything they want. All you need is 1 and 90 degrees.
You define the value.
You say, what is 1? And why am I doing that? Because it gives them sense about measurement. Right? I'm saying that this is 1. Who cares how much it is, how long it is? I say this is 1. Right? If this is 1, this is the square root of 2. And see, this is, they make different drawings, different sizes, and each drawing has this statement in it. If this is 1, this is the square root of 2. For each paper, right? In other words, this is the square root of 2 when this is 1. Right? Look at this. When this is 1, this is the square root of 2. Do you notice the measurement and number sense I'm giving them? You see? When this is 1, this is the square root. When this is 1, this is the square root of 2. And when this is 1, this is the square root. Powerful stuff, right? When this is 1 right here, this is the square root of 2. And I can give them all kinds of examples, right? You know, I mean, by itself gives you 3. So you have the students build this figure. They love drawing this figure. They just love it. Hopefully they have developed the dexterity to do it, because it's not easy to be precise. But there are some good things that you can get out of here. This length is 2. The number that multiplied by itself gives you 4 is 2, right? And if you keep going down here, you're going to get the square root of 9, and the length of the square root of 9 is 3, because the number that you multiply by itself gives you 9 is 3. So the Greeks also had this kind of construction. I think it is in the elements, you know, Euclid's elements. I'm not positive, but I think it's there. Okay? The elements were written around the 4th century, but they were a collection of the last 1,000 years of mathematical knowledge. I mean, Euclid is the first one that made that good book. There were other books, but they were lost. The Elements is almost the only good, complete book that we have of this kind of stuff, and that's why we base our, you know, the Greeks did this, the Greeks did that, because Euclid wrote it in a book. Later, not when it happened, you know, much later. So again, this is the kind of thing that the students go home and show to their parents. I mean, they're like, look at this, you know, it's awesome. And again, you're reinforcing the Pythagoras theorem, that kind of stuff. So this is day 7. In day 8, you're going to do this activity now. And I'm going to ask you to make these 2 squares in this other paper. To draw these 2 squares, you have to use the paper in landscape mode. That means like this. So please draw those 2 squares right there. This is one square. This is one of the squares. Okay? This is the other square. And this is just one point that I need for the construction. Okay? So this is one square, and it's not called square A. This is point A. Okay? This is one of the squares. This is another square, and I also need point C for some reason. And this is just the point that I need. So please just draw the 2 squares, and then we'll do something with them. This is in, it's not right, okay? I mean, yours
Oh,
is
okay.
like this. You know?
All right, yeah.
Yeah.
Right.
So after you make this drawing, you should come up. This is the way it should look. There is a large square, and there's a smaller square that lies next to it, and point B. This point B is the result of getting this length and transferring it over here. Okay? That's what point B does. It gets this length, it gets this, actually I put it in the wrong place. Okay. Point B is the result, right, of getting this length and bringing it down here, right? So it looks something like this, and then you're asked to connect point A to B and point B to C. And your drawing should look like this. Okay? So now you have 5 pieces. Okay? 1, 2, 3, 4, 5. Right? 5 different regions. So this is another proof of Pythagoras' theorem that the students are asked to do in a tactile form. Meaning that you're going to ask them to draw this, and the activity where they're going to spend a lot of time, sometimes days, sometimes weeks. Okay? The activity goes like this. After they draw that, you ask them to cut the pieces. These are the instructions for the second part. Label the 5 different areas so you know which side is up. The reason that is there is because usually I use just white paper. You have to use cardstock, thicker paper. But usually it is white. It's not lined and anything. So when they do this figure, it's just sitting on the paper like this. So they have to label it so that they know which side is up. Because if you flip one of these pieces, it doesn't work. They must be in this. So you cut the 5 separate areas, and you use all 5 pieces to form a larger square in a regular puzzle mode. Now, why does this work? Let me show you why it works. This is the triangle we're working with. It's a right triangle. This side squared is this side, this square, right? And this side squared is this square, right? If we square this side, we get this square, right? So we have the squares of the 2 sides right here. And this is the hypotenuse. The larger square has to look like this. Of course, you're not going to tell the students this. But that is the square that you can make with the 5 pieces. Now, let me tell you something. I had a group of motivated, advanced students, kind of advanced 7, 8 graders, 6, 7, 8 graders. And I gave them this puzzle at the beginning of a summer session. And the family of one of the students came back 6 weeks later. 6 weeks later. And they said, Mr. Salazar, it can't be done. Something must be wrong. So then I said, show me they said, everyone in the family has tried it for hours. It doesn't work. I said, okay, well, show me the pieces. They showed me the pieces, and I put them in this form just to make sure they were working with the right set. And then I showed them right there how to make the large square, and they could not believe it. I mean, it's the most amazing thing in the sense that it's so complicated. And there's only 5 pieces. And you're only making a square. I mean, how complicated could that be? Well, it takes the students 20, 30 minutes, days, weeks to do it. Now, interesting facts. This proof of Pythagoras' theorem was discovered in the 19th century by some guy. Okay? And later on, in the 20th century, it was dug out from the ruins of some Greek city. In the 20th century. So it turns out that some Greek guy had discovered this proof 300-400 years BC. And this guy discovered it by himself in the 19th century. So he got credit for it too. Because he couldn't have seen it because it was dug out in the 20th century. No one had seen it ever. And so he got credit because he actually made it public in the 19th century. But it turns out that someone had already done it. Now, the nice thing about this proof, because there are hundreds of proofs, the nice thing is that it's a very nice classroom activity. It lends itself to the classroom very well. So, this is your challenge. Cut the 5 pieces and make the puzzle. Just so that you get an idea of how complicated it is, okay? If days go by, email me and I'll send you the solution, okay? So another proof where the students get to draw, they get to cut, they get to work with the puzzle, but it's a very significant mathematical puzzle, right? Day number 9. So, the Pythagorean group. Remember that group of people that I told you that believed in the numbers and this and that, religion and so? Well, they were called the Pythagorean group. And they were like a religious sect. They were secretive, they didn't tell people what they were up to. And they came up with this problem and they worked on it for years and years and years. And finally, while some of the brothers were trying to find out a fraction like this, remember they were trying to find out something like that? Well, they tried, and then one of the brothers started to work on something else. One of the Pythagoreans, one of them came up with this proof. Okay? And this is how mathematicians prove things sometimes. They said, let's pretend that the square root of 2 can be written as a fraction. Now this fraction right here is in lowest terms. Okay? It doesn't have any common factors. Okay? So this has to be in lowest terms. So that means it's reduced, it's simplified. It's not a fraction of this kind. It is not a fraction of that kind. Because this is not in lowest terms. It's a fraction of this kind. Something like that. Okay? It's reduced. So if I square both sides of the equation, the number that this is the number that if you multiply it by itself gives you 2. So if I multiply the number by itself, I get 2. If I square this side, I get a squared over b squared. Okay? If I bring this divisor to multiply over here, or if I multiply times b squared, these two b squares cancel each other, and I get 2b squared equals a squared. Now, this number right here is an even number. It is an even number because it has a 2 as a factor, right? even numbers by definition can be divided by 2, and this number can be divided by 2, right? So it's even. And it turns out that the square of an even number is an even number. So this number right here must be even. Okay? If this is even, this A must be an even number. Okay? Like for example, 2 squared gives you 4. 3 squared gives you 9. But 3 is not an even number. Right? 4 squared gives you 16. Even. 6 squared gives you 36. Even. And so on. The proof is not easy. But you see how it works. So it means that A is an even number, which means that it has 2 as a factor. If A is an even number, it means that it can be divided by 2, which makes it an even number, right? Which means that it has 2 as a fraction, as a factor. For example, the number 2 is even. 2 times 1 is 2. The number 4 is even. 2 times 2 is 4. The number 38 is even. 19 times 2 is 38. So it has 2 as a factor. That means that A is even, right? I'm coming back to here. If I substitute this number in here, because A equals to K, right? And I work it out, I get 2b squared equals 4k squared. 2k times 2k is 4k squared. Which, if I simplify, that means if I divide by 2, I get b squared equals 2k squared. Since this number is even, then b must be even, right? Like I proved before, right? B must also be even. So that means that contradicts. These two numbers cannot be both even, because then they wouldn't be in lowest terms. Right? If these two numbers are even, A and B, it means that this fraction is not in lowest terms. Right, so it contradicts what I started with. It means that this whole thing is not true. It means that this is not possible. Okay? And this proof is attributed to the Greeks. The guy that showed this was thrown overboard. Because it proved that, to them, it proved that God had made a mistake. Nonetheless. That exactly, they said this is not possible. And they actually threw the guy overboard, and they maybe even threw his papers overboard. They didn't want to see it even. But you know what they say about progress? Believe it or not, some people call this progress. It couldn't be contained. Someone else figured it out. And so now we have the number that when you multiply by itself, the answer is 2. The number that when you multiply by itself, the answer is 3. But that doesn't stop there. The number that when you multiply by itself, the answer is 1.3. If these numbers are complicated, you can imagine that one, right? In reality, they're just equally complicated. They're numbers that never repeat and never end. And they have a name, actually. They are called irrational. Not because they're crazy. It's not because they're crazy, right? Why are you being so irrational? That's the way I am. No, it's not because of that. It's because they cannot be written as a fraction. Okay, that's the reason they're called irrational. Any questions? Comments?
It's like sitting in a college class 4 years ago.
So, I mean, I get this reaction from teachers, usually. Students need to be given these kinds of lessons. I mean, of course, you have to think about it carefully. But this is the most complicated thing I did today, mathematically speaking. This proof is at an 8th grade level, right? I mean, because I was working with equations and stuff, and I was working with this theorem, the fact that the square of an even number is an even number. Okay, so those two things, they have to be accepted on face value. But even when I say let's square both sides, if I say, right here it says 3 equals 3. Let's square both sides. 9 equals 9. Isn't that true? Let's say this is 4. 4 equals 4. Let's square both sides. 16 equals 16. You see how it works? That's another thing, that when you tell them things like that what all this means is something like this. 2 equals 2. 4 equals 4. 2 equals 2. 1 equals 1. 5 equals 5. Right? That's what this whole thing means. What it means here is that whatever this is, the other side is. So if this is 3.2, this is 3.2. And that's one fact that escapes most middle school and even high school students, the meaning of the equal sign. And this explanation is an opportunity to emphasize this. Another thing is that after going through the lessons, they're more willing to let you show them this. Because I got that far with my 8th graders. Of course, they said, it was like I was doing magic over here in front of them, right? I mean, they said, well, yeah, whatever, sure. But it is a real proof. I mean, some of them, what I expect is that they are able to follow my reasoning. I don't expect them to be able to explain it themselves or to remember it even. But some of them are able to follow your explanation. Okay? So, thank you very much. Okay, so now here I have the end of the presentation and my emails there. The handout, I'm going to give you this, so you don't have to write it down, I'm going to give you a handout of this stuff. And then I even had a joke in here for the end of the presentation that I want you to see. I don't know why they put those pages in books, right? They say this page intentionally left blank. So what? I mean, like if people worry that something should have been there, right? So I have like I said, how the square root of things of the first few numbers.
Second presentation.
You can keep doing this. Okay, so now we had a proof of Pythagoras theorem. Using Pythagoras theorem, now we construct the square root of 2, 3, 4, 5, 6, 7, 8. And now I'm going to ask you to do another thing that is a lot of fun for the students. that I want you to do on this other paper. I'm asking you to draw those two squares. Okay?
Good afternoon, and pardon the interruption.
This is one of the squares.
We apologize for the interruption to your workshop.
This is a square right here, 4 points. This is another square.
We thank all of our participants for your willingness to spend the day in a community of
So I ask you to draw two squares in landscape mode. Landscape being this way. And you should get a figure that looks like this. Two squares adjacent to each other, one larger than the other. Okay? They should be square and they should be sitting right next to each other on a horizontal line. The result of finding point B and doing what it says on the bottom, connect points A to B and B to C, it should look like this. Please look over here carefully. The result of that is that if I get this length, and I find it over here, this point is point B. Okay? This is point B, and this is point A, and this is point C. So now I'm going to connect point A to B, and B to C. And I should have a figure that looks like the figure that I have over here, with 5 separate regions. 5 regions. So this is another proof of the Pythagoras theorem that you want the students to do. This is a very interesting puzzle. It turns out that if you cut these 5 pieces, you can make a large square using the 5 pieces. And the reason is this. This right here is a right triangle. Okay? This is the square of this side. Isn't that true? This is the square of this side. And this is the square of this side. Isn't that true? This square is the square of this side. Because remember I brought it over here. The size of this square is translated over here. Right? So this square is the square of this side, and this square is the square of this side. So the sum of the two squares must be the square of the hypotenuse, right? So there must be a square that looks like this that can be made with the 5 pieces. Okay? So it is a proof of Pythagoras' theorem, but if you cut the pieces and you've never done it, it'll take you anywhere from 10 to 15 minutes to a few days to be able to make the square. Teachers usually are able to make the square after a few tries, because I told you the square you should make. I had a student family come to me after 6 weeks and say, Mr. Salazar, you made a mistake. This is not possible. And I say, okay, show me the pieces. So they showed me the pieces, and I put them together like this to make sure they had the right pieces, right? And then I made the square in front of them. They could not believe it. They have been trying for hours for 6 weeks. And it's amazing that there are 5 pieces and that you have to make a square. One of the simplest figures in existence, right? Yes?
Isn't that 3 and 5 with that?
3 and 5 go.
Let's say that point.
Well, you see, this piece right here goes right here.
And then next to it.
And then this one goes right here, and then
Right,
this one goes right
right.
here. Yeah, well, I told you the square to make. If I hadn't told you that, it would be more difficult.
Have you seen, there's 2 of them now, visual proofs?
Oh yeah, there's
There's a number of.
there are other pieces that are. The good thing about this proof is that when you do it with the students, you don't tell them what you're doing. It isn't until they find the answer that you explain to them why it works. Because you already did these other lessons.
Well, the books have visual proofs of.
Oh, there are, yeah, there's some.
Different, from not only geometry, but trading.
Like in Lucy training, they use 2 of them. And you know, there are a lot of proofs, and some of them are better than others to use in the classroom. Because what I want is the students to be able to make the papers and the stuff. Okay, so this is one of the. So the next transparency tells you what I just told you. The next slide tells you what I just told you. And I encourage you to do it. Label the 5 different areas so you know which side is up. And the reason is that we usually do this on blank paper, not on coordinate plane paper. Carefully cut the 5 separate areas. Use all 5 pieces to form a larger square in regular puzzle mode. Good luck. It's not easy. It takes a little while. Of course, I already explained to you how to do it, but give it to your students and watch them struggle. The struggle is very important because of this. You have 5 pieces in front of you, and you are going to make a square. Do you understand? Yes. It's too hard. Yes, it is too hard. But you know what you're doing, right? You're going to make a big square using the 5 pieces. Do you understand what you're supposed to do? Yes. You don't want to do it? Fine. That's a different problem. But everyone understands what needs to be done. Okay, that's the beauty of these things. They develop patience. Yes?
And that you are already letting them draw those 2 squares, draw that triangle, and then cut them.
Right.
And then, once they're mixed, they have to build up this.
They have to make a big square with the 5 pieces. Yeah. Exactly. They're going to cut. See, that's the thing, that you give them this, I mean, First, you make sure they made the drawing correctly. Again, there are two squares. It's very easy to see if they're square or not. Right? And once you know that they did it correctly, then you tell them to cut the pieces and make a version. And usually, they have to take it home and keep working on it. And they come the next day and they say, "Mister, it can't be done." And, you keep telling them, just keep working on it. It can be done. I believe you me. So, after a while, they start to get the answer, because once one of them does it, but some of them, they resist the temptation to get the answer worked out. And finally, the Greeks, one of the Pythagoreans found the proof that the square root of 2 cannot be written as a fraction. And you know what happened to him, right? They threw him overboard. Someone wrote this proof and they say, evil,
That was actually
blasphemy, threw him overboard with his papers. But the proof came up later on anyway. It couldn't be stopped. Let me go through the proof. Proof by contradiction, accessible to average algebra students. Meaning algebra 1A1, 1A2 students, they should be able to follow you. Okay? The square root of 2 equals a fraction. Let's pretend that's true. If you square both sides, you get times the square root of 2 times a over b. Remember that this is the number that when you multiply by itself, the answer is 2. There it is. When you multiply by itself, the answer is 2. That's what we were talking about all these days, right? A over b squared gives you a squared over b squared. If I multiply times b squared, these two b squares cancel each other, because b squared divided by b squared is 1. And I get 2b squared equals a squared. This number is even because it has a 2 as a factor. And even squares, the square of an even number is an even number. It means that a must be squared. It's one of those theorems that work both ways. If this is even, this is even. If this is even, that must be even. Okay? So, because this is even, a must be even. Now, when we wrote the square root of 2 equals a over b, this is supposed to be in lowest terms. Okay? It cannot have common factors. It's in lowest terms. So we found out that a is even. Now, if I go back, if a is even, it could be written like this, right? If a is an even number, it must have 2 as a factor, right? So I could replace a right here with 2k. You see this a, I'm replacing it with 2k. So now I have 2b squared equals 4k squared. If I divide by 2, I get b squared equals 2k squared, which makes b even also. Which is nonsense, because I said that this is in lowest terms.
Can I borrow 2 chairs?
Right? So that means that this whole thing is wrong. The reason it's wrong is because this is not possible. Everything else is fine, but this is not possible. So in other words, you cannot write the square root of 2 as a fraction. And this is pretty much the proof that one of the Pythagoreans found. I think this kind of explanation is in Euclid's Elements.
It's the name. It wasn't true.
No, he just brought everything that everyone knew up to
There's
this.
a theorem that somebody had, I forgot what they call it, that nothing in math is named after the person who really discovered it.
Right. Well, yeah, I mean, you can, I mean, other people had written this stuff, but, I mean, it just happened that his book is the one that survived the best. Yes, it is. So,
Well, you can keep it or?
No, no.
are there any questions or comments?
Thank you, this was very nice.
Okay. So, let me give you the handout of the presentation. In my email, it's a small, yeah, it's a very small document, so there shouldn't be any problem.
Thank you very much, Mr. Salazar.
You're welcome.
Very good.
My pleasure.
You can have
Nice to meet you.
it.
Okay, great.